started on the Unit 3 project on momentum. So to start with, can somebody let me know if you can see this? Just unmute your microphone and tell me.
Yeah, you can.
I can see it.
Perfect. So the first thing to do, of course, is put your name in here, right? So don't forget to put your name in there. Another thing that you might like, it's up to you. If you want to see every comment that you're making, well, then keep this open. But if you'd rather just get it out of the way, you can just use this arrow right here. And it kind of gives you a little more space to work with. Although I think I've zoomed in a little too much, so I'm going to zoom back out. Up here, we can zoom in and out. Okay, so as you know, we're studying momentum, and hopefully you're starting to memorize this equation, P equals mv. P stands for momentum, M is for mass, and V is velocity. And I don't know if you've ever seen any of this artwork by M.C. Escher, but it's pretty amazing stuff to look at. And it's actually quite mathematical. And so we're going to be making use of our mathematical skills, and we're going to be thinking in terms of making computations, of computing things. We're going to use the greatest computer of all, which is the one between your ears. So as usual, this project begins with some kind of interesting cover and just kind of a little appetizer of what else is out in the world to learn about. Here's another one of Escher's artworks. So let's talk about him briefly. The cover art for this unit is by an artist named M.C. Escher. Moritz Cornelius Escher was born on June 17, 1898 in the Netherlands. He was the youngest son of the civil engineer George Arnold Escher and his second wife, Sarah Gleichmann. As you can probably see, Escher's art is based on mathematics. His originality and mastery of graphic techniques are respected, but some people think his work is too intellectual. However, his use of perspective made his work very interesting to the public. What do you think? Look again at the front cover of this unit. Follow the waterfall as it turns the water wheel and then flows back to the top of the water. Wait a minute, that can't be right. The water channel looks like it's level, but there is clearly a change in elevation between the waterfall and the water wheel. Why do you think this piece of art is called perpetual motion? Escher was quoted as saying, "The flat shape irritates me." So let's look at this again. It's pretty wild. First of all, he used perspective a lot, which gives things kind of a three-dimensional appearance. You can see these terraces in the background, and you can see that this part of the water channel appears to go further away from us, and this part comes closer to us. That's perspective, and you'll probably learn about that in art class. But let's look at this water. Here it is, a waterfall's falling down, and that's giving energy to turn this water wheel. We could talk about this in terms of physical science too. And then the water flows along the channel away from the water wheel, follows the water channel, follows it. Well, wait a minute. Didn't we just go uphill? Can water possibly flow uphill? What's going on with that? Well, really, Escher was really good at at tricking our eyes, basically. So when we look at this, it looks like it's going downhill, but then it ends up at the top. And I think part of it is the way he treats these columns. Look at this one. It looks like it's just on top of something, but here it ends up underneath something, huh? This one was on top of this part of the channel, but then it's under this other part of the channel. And by doing that, he tricks our eye into thinking that everything's going along just fine, but obviously this is not something that could happen in reality. So it would just keep going and going and going, giving it the name perpetual motion. In fact, there's long been a search for something called a perpetual motion machine, which would mean you would never have to add energy to it. You could get energy for nothing. Well, as we know, that doesn't quite work that way. Can't get energy for nothing. Anyway, Escher also developed the process of tessellation, where a flat surface is covered with interlocking shapes without any gaps or overlaps, as shown in this image up here with the fish and the birds. In your spare time, color the image for extra credit. Can you keep the fish and birds separate? Bonus points for designing your own tessellated drawing. So if you want to follow up on that, you're welcome to. You don't have to. I think Escher's work is pretty amazing. It's pretty famous. I'm sure you can find plenty of images online if you look him up. It's kind of fun to look at these things and try to figure out how he made the impossible seem possible. At any rate, let's move on to our actual project here. And this one, momentum equals mass times velocity, that's a key idea. We also have a couple of other big ideas here at the top, and I'm looking for a volunteer to read this first one for the group. Who's going to step up? Come on, somebody read for us.
Which one is it, Mr. Fairley?
Just this first question, how can I?
Oh, okay. How can I use mathematical representations to support the claim that the total momentum of a system of objects is conserved when there is no net force on the system?
Is that Sam?
Yeah.
All right, thanks for being here. I saw you checked in early, but then you left and you ended up late.
Yeah, sorry.
So be here, okay? But you get extra credit for participating. Thanks. So one of the big questions we have for this unit is how to use mathematical representations, in other words, equations. How do we use math to support this claim? How can we provide evidence that the total momentum of a system is conserved? Now remember, when we conserve things, we're saving them. Remember, we talked about the law of conservation of energy. Well, that's just the first of several conservation laws. There's also the conservation of mass, and as we'll see in this unit, we also have the conservation of momentum. And they're all very similar. It basically means you can't create or destroy something. So with conservation of energy, we can't create it, we can't destroy it, but we can change it. And the same thing is true with momentum. At least we can't create it or destroy it when there's no net force acting on the system. We're going to talk about that more in a minute. So the momentum is retained unless a force acts upon the thing. Does that make sense? We keep the momentum going unless some kind of force interferes with the momentum. All right, anybody want to volunteer to read the second one? Pretty sure.
Go.
All right, who's this?
Kitsali.
Thank you, go ahead.
Boundaries and initial conditions need to be identified when investigating or describing a system.
Okay, thank you, and you get some extra credit points for participating. So boundaries and initial conditions need to be identified. So we're going to study this system of Newton's cradle to begin with in order to learn more about momentum and collisions, because don't we have collisions between these balls when we drop them? So when we study a system like this, we have to start by setting some boundaries. We got to have a boundary in here, something that limits our study. For example, really what we're trying to do is limit our study of Newton's cradle to this boundary here. I didn't draw it very well. This is the boundary of our system, because all we're interested in is the momentum and the velocity and the mass of these balls as they're moving. So in this boundary, you might wonder, but wait a minute, we took the ball way up here and then it went flying way out of here. It flew out of the boundary. Well, we had to draw a limit somewhere. And the reason we made that be the boundary is because the velocity is what I'm creating by lifting this. But how did I do that? Well, by lifting it, that means I involve my hand. But wait a minute, where did my hand get the energy to lift that? Oh, it got it from my breakfast. Oh, but wait a minute, where'd that energy come from? Oh, it came from the sun. Oh, and you can see this just goes on forever. So we have to draw the line somewhere. We have to place a limit on our system in order to really be able to investigate it. And the nice thing about choosing this, is that we're just looking at mass and velocity. The mass is going to be changed by the number of balls we lift up. The velocity is going to be changed by whether we only lift it a little bit or whether we lift it higher. And then that velocity is created as it falls, and when it enters the boundary of the system, I should have done that like this, I think would have looked better than yeah, that's better. When it enters the boundary of the system, it has the velocity that we're studying. We're not really interested in the height. We are interested in the velocity, but we don't really have a way to measure velocity. We can measure height. That's pretty easy. And the higher we lift it, the more velocity we get. It'd be awesome if we had like a cop's radar gun that we can use to measure the velocity as this thing comes in here and measure the velocity as it exits, because that's what we're interested in. So the boundary of this system is basically right here. So that's boundaries. Next, initial conditions. This is our starting point. So here's our initial condition over here, the beginning of the experiment or the study or the analysis. We call that the initial condition. So in fact, what I would like you to do is label this as initial conditions. Initial conditions will include how high we lift it, how many balls we choose to lift, whether we lift it from the left or the right, things like that are our initial conditions. Then we let go and the ball falls down. So let's put an arrow in here, and you can either draw it with a pencil or maybe you can put an arrow in like this. I leave that to you to decide. The ball comes down here, and then let's show what happens over here also. Add another arrow on this side. Now this is what happens after we release it, right? This is what we're measuring. So this is our response or our response conditions. So let's put that on there too. Our initial conditions are where we begin. Our response conditions are what we're going to analyze. So you should have 2 arrows and 2 labels on this diagram of the cradle now. All right, do I have another volunteer to read for us?
I'll read.
All right, who's that?
Andres.
Okay, thank you. Just the first line.
Newton's cradle was designed as a fun distraction for executives in the 1960s. It's based on the physics of momentum and collisions. The image above shows several details.
Great. So this thing was set up as a toy, basically, for people working in an office back in the 60s, and they'd have it sitting on their desk and play around with it, I guess. So anybody else want to read the next one?
I'll read.
And who is this?
Vanessa.
Thank you.
Yay. The cradle includes 5 steel balls of equal size and mass, hanging motionless and just barely touching each other.
Okay, ideally, they're equal size, they're equal mass, they're not moving, and they're barely touching. And I might also add, they're in a straight line. Like the one I have isn't quite in a straight line, is it? So, at any rate, good job, Vanessa. Do I have another volunteer for the second bullet down there?
I'll read it.
Thanks. And who are you?
Armando.
All right, take it away.
The diagram on the left side uses solid lines to show a ball lifted before it's released.
Okay, go ahead, do the next one too.
The dotted diagram on the right shows a ball responding after the first ball was released.
Okay, great. Thank you very much. So can you see that this is kind of like before and after? We're showing before as solid diagram, after as a dotted diagram, okay? That's kind of a standard approach to these diagrams. So we've already added arrows and we've already labeled the before and after positions with initial conditions and response conditions, right? Should have an arrow here too, huh? I'm going to let you draw the arrow in the correct direction, show the correct vector. Now, what I want you to do next is think of, for yourself, and we're all going to have different ones, I want you to write out 3 questions that we could investigate about this cradle. Any 3 questions that we could study about this cradle. So you get to do them yourself. We looked at a lot of options yesterday, right? So go ahead and fill out 3 possible questions. All right. Alex, thanks for joining us. Alex D. Who else am I looking for? Did Lena ever arrive? So if you came in late, we have downloaded Unit 3 project, Unit 3 project. It looks like this. So if you figured that out for yourself, well done. If not, go to the assignment, download this, and we're just getting started on the actual project itself. So just as a reminder, let's see, I don't know how well you can see this. Oh, I know, I should just turn off my background. Okay, so one question where we started was something like, what happens when we left one ball to a medium height and let go? That could be one of your possible questions, except that was the question I just asked, so you have to come up with something different. We also changed the number of balls, right? We also changed the height from which we dropped them. So I want you to come up with any 3 questions, but I do want to put a limit on it, which is that at least one of the questions should involve changing the mass. To do that, we have to change the number of balls we lift, right? So one of them should involve changing the mass. One other question should involve changing the velocity. To do that, we have to lift it higher for more velocity or less high for less velocity, right? So any 3 questions, but one has to involve changing mass, and another has to involve changing velocity. And then when you finish writing out your 3 questions, please give me a thumbs up so I know that we're ready to move on. All right, good job, you guys. Couple more minutes and then we'll move on. All right, good job. I'm going to go back to the actual assignment here. So you should have written out 3 questions about different ideas of what we could explore, basically. What happens when we lift one ball to a medium height was my first question, and you needed to come up with 3 others. At least one of those changes the mass by changing the number of balls, and at least one of those changes the velocity by changing the height. Okay, so what I want you to do, notice that we're repeating these big ideas, the equation for momentum and the 2 big concepts for this unit on every page. So every time it's a reminder that we're trying to figure out how to use mathematical representations to support the claim that momentum is conserved. And a reminder that we need to look at boundaries and initial conditions. So what I would like you to do is take a couple of minutes and I want you to highlight the important text on this page. All right? So yeah, just finish this page and then give me a thumbs up so that I know we're ready to move on, okay? Highlight the important text on the entire page 4. So give me another thumbs up when you're done reading. Great. And if you haven't noticed before, realize that I do look for your highlighting when I'm scoring these, huh? So we want to look for the most important stuff and highlight that. At any rate, this kind of repeats some of the stuff we talked about. Solid lines for before, initial conditions. Dotted lines for after, the response conditions. We have a boundary of our system. And notice that the system is not doing anything at first. The balls are just hanging there, huh? Until we lift up one of the balls and drop it. That's what we mean by applying a net force. So this is an external force outside of the system that we are applying to these balls. They were just sitting there minding their own business until we came along and applied a force to this one and dropped it. And that velocity coming in is what's shown by this vector arrow right here. So the velocity coming in is the beginning of the system that we're studying. The velocity going out is the continuation. And you can see that these two arrows are about the same length. The ball at the beginning ends up about the same height as the ball at the end because momentum is conserved. Now with my Newton's cradle, as you saw, it's kind of beat up. And so this ball is probably not going to make it as high as the initial release because it lost energy along the way. My balls are not completely hanging in a straight line. And they kind of bounce around a little bit. So anyway, we're going to do the best we can with that one. Basically, we are looking at three variables in the system. The mass, which is how many balls we lift. The velocity, which is how high we raise those balls. That changes the kinetic energy. That changes this velocity. And finally, whether we lift them to the left or the right. And you might not think that that's very important, and it might not be, but we should just keep in mind that that is one of the variables we are modifying. Okay. Now, we're moving on to actually designing our experiment on page 5. So go ahead, you can jump to page 5 by using these arrows, or you can scroll to it. But what we have to do is plan our experiments first. And we're going to do 4 of them. First is one that I'm designing, and then you're going to follow up with 3 experiments that should answer your original questions. So we have to plan the experiments. First one, set up. Make sure that your 3 experiments will answer your 3 questions. Include all the details of what you will do. Someone else should be able to follow your instructions and repeat your experiment. So let's look at mine. Remember, my question was, what happens when one ball is dropped from a medium height? So the first thing what I need to do is record the initial conditions in the data table. That is on page 6. Here's our data table that we're going to be filling in. And I've already filled in some of the initial conditions in experiment 1. First trial, if there's going to be a drop height of 3 centimeters from the left, and it's going to involve 1 ball. We're going to fill this in later after we actually measure their mass. We actually did that yesterday, but we'll do it again when we actually do the experiment next class. On this side of the data table is where we will record what happened, the response. So this is the before, this is the after, right? So the first thing to do in the experiment is record initial conditions. Then I lift 1 ball 3 centimeters high on the left. Then I release it without pushing it. Then I'm going to count how many balls respond and measure their maximum height I decided that this needs one other thing here, though. I'm going to measure their maximum height on the first swing. It might not be very important if we had a really good Newton's cradle, but again, mine is not very good, and it seems to lose energy pretty quickly. So I want to measure the amount of energy at the best possible moment, which is on the first swing. Then I'm going to record my response conditions in the data table down here, like I said. I'm going to repeat this 3 times and find the average. And finally, I'm going to draw a vector diagram showing the system boundaries, the initial conditions, and the response conditions. So I'm going to repeat this same experiment 3 times. So here's going to be trial 2. Here's going to be trial 3. Then we're going to do a different experiment. And we're going to do that 3 times. Whoops, not 23 times. 3 times each, right? We'll take the response height, whatever this came out to be. We're going to take those numbers and we're going to record them on the next page and find their average here. And this is where we'll draw the vector diagram. So right now I'm kind of giving you a preview of coming attractions. We're going to plan the experiment today. We're going to conduct the experiment, gather the data, and analyze the data next class. All right. So what I would like you to do is design your own procedures to answer your 3 questions. Basically, you take the question that you wrote down up here. Question 1 is going to become experiment 2. Just repeat that question there. You can rephrase it if you want. And then you need to write out a series of steps of what we're going to do to answer that question. Do the same thing for your other 2 questions down here as experiments 3 and 4. Give me your procedures to answer your questions. So we're running out of time for you to finish. This is basically your homework assignment, is to finish writing out these questions and procedures. And then when do I see you again? Is it Tuesday, I think, because of the new schedule? Yeah, I think so. That's when we'll actually conduct the experiment. So you have until next class to get this page finished, finish page 5 on your own. Now, some of you might like to see what that schedule looks like. Maybe you haven't seen it yet. So I have that for you here. You might want to take a photo of this. So can you see that okay?
Yeah.
Yeah.
Okay, great. So if you want to take a photo of that, you can, and you'll have a copy on your phone. What are we? We are 5th period, is that right? Yeah, so we'll be meeting at 8:30 in the morning. That will be Tuesday, is the next time I'll see you. So we'll have an hour every morning for your first period, whatever that might be, academic success class, etc. And then we start the rest of our classes, huh? Monday, you just have 1, 2, 3, 4. Tuesday, 1, 5, 6, 7. Every day we have first period. Okay, and that's all I have for you today, unless you have some questions for me. You are free to leave and work on designing your own project. Excuse me, not designing your own project. Design the experiment that will answer your question about Newton's cradle.
All right, bye, Mr. Finley.
Okay, I'll see you later.
Thank
Thanks for coming. Have a good weekend, you guys.
Bye,
Thank
Fairley.
you.
See you, Mr. Fairley.
See you Tuesday.
Bye, Fairly.
Bye, Fairly.
Bye.